Yeah.
Yeah.
What do you have?
All right. I had one on 2.5, number 22.
Okay, both parts,
I think it was just the first part.
the first part, so the end behavior for that function. So as a reminder, when we're asked to compute end behavior, they sort of spell it out there for us. But when we're asked to compute end behavior, we need to evaluate the limit at infinity and negative infinity. We need to check both ends. If you're savvy, you remember a specific type of function where end behavior, it suffices to check just one end. What kind of function was that? Rational functions. So when we have a polynomial divided by a polynomial, you can compute one or the other, and they'll tell you the same information. Remember, rational functions have, at most, one horizontal asymptote. But any other function, you want to look at both limits, infinity and negative infinity. So this is if you go on to Calc 2, you'll see a little bit more about these hyperbolic trig functions. And remember the circular trig functions just give us a point on the unit circle. Hyperbolic trig functions would give you a point sort of on the unit hyperbola, which was x squared minus y squared equals to 1 instead of x squared plus y squared. So it's a direct analogy to finding points on a hyperbola. But anyhow, they tell us that the hyperbolic cosine function labeled cosh x is used to model the shape of a hanging cable. They're called catenaries, like a chain hanging between two poles, or certain types of suspension bridges have that sort of hanging wire shape. And they tell us that the function is actually defined as the following, which is, we see it's an exponential function. Even though we call it a hyperbolic trig function, it's really an exponential function. And they want us to determine the end behavior for the hyperbolic cosine, so that we need to compute the limit at infinity and negative infinity. So with some of these, like we saw last class, I think you can think about them sort of symbolically. If x is approaching infinity, then that's e to the infinity plus e to the negative infinity all over 2. And so what is e to the infinity approaching? All right, that's just some positive number, 2.71828. Getting larger and larger powers, so it's going to get larger and larger. How about e to the negative infinity?
0. Number getting smaller and smaller.
Smaller and smaller, right? Okay, so let's continue looking at it symbolically. We have infinity, we have this thing approaching 0 all over 2. So what would infinity plus 0 over 2 approach?
Infinity.
Infinity, okay. So the limit on the far right, as x approaches infinity, that function goes off to infinity. So we don't have, that doesn't give us a full-scale picture of what that function looks like, but we do know that when we're way out here, that the hyperbolic cosine is way up here. Right? So as x gets larger and larger in this direction, the function gets larger and larger in that direction. Okay. And I think with that in mind, you can compute the limit at negative infinity, because it'll be very similar. So does anyone have any questions or comments on that? Yeah.
Can you show us how e to negative infinity is approaching 0?
Yeah, so we can think of it in a couple of ways. You can think about it visually or algebraically. So e to the negative infinity, that has to be in the context of the limit as x approaches infinity. of e to the negative x, or the limit as x approaches negative infinity on e to the x. So either way, so when we write that symbol, that's what we're meaning. We're not evaluating at infinity because we can't do that. Okay, so if we think about, let's think about it algebraically. If I'm just thinking about this as e to the negative infinity, writing that with positive exponents, I write that as 1 over e to the positive infinity.
Right, which is 1 over 0, which is...
Right, yeah, exactly. 1 over something, a fixed number over something that's getting smaller and smaller is something that's getting larger and larger as a quotient.
That's definitely
Yeah.
0.
Okay, cool. Yeah, and then if you think about just the graph of e to the x, as I approach negative infinity, it approaches 0. So there's a couple ways to think about it. I think more likely in practice, you want to think of, you're probably using that strategy to think about it, because when you are computing limits, a lot of times we are plugging stuff in directly. So, but either way is sufficient. Any other questions or comments about this problem? Let's see. So part B says evaluate cosh of 0. So again, we're just going to default here to the definition, plug in 0 for x, and see what we get. And then it says use symmetry and the end behavior found in part A to sketch a possible graph. So once we know the limit at negative infinity, we're going to get this end behavior over here, whatever it's doing, over here, over here. We're going to evaluate it at 0 to see where the point's at. Is the point here? Is it here? Like where is it at on the y-axis? And then symmetry. Who remembers symmetry? What is symmetry? What do we mean when we say symmetry?
It's like what's happening on either side of an axis is like the same from like if you have a set point, and then if there's a point 4 points to the right and there's a point 4 points to the left.
Yeah. Right, so symmetry, it really depends, but as far as like functional symmetry, we talk about 2 types of functions, which was an even and an odd. Do y'all remember that? Even and odd functions. So you test for symmetry that way. Yeah, and so symmetry itself is kind of generic. I think we all know what symmetry is, just in a very vague sense. But in a mathematical sense. Just as a reminder, symmetry with respect to the y-axis. If I have a function that's symmetric with respect to the y-axis, what kind of function is that?
Even.
It's an even function, like x squared. Think about x squared, x to the second power. That's an even function. Meaning that the original function is equivalent to f of negative x. In other words, if we replace all of the x values with negative x values, we're still on that point, on that function. So again, think about x squared. The point 2, 4 is here, but also the reflection across the y-axis, negative 2, 4 is here. So that's true for all of those points. And then we didn't really look at, as far as functions go, we didn't look at symmetry with respect to the x-axis because why?
It's not a function.
Yeah, it's not a function, right? If you have symmetry with respect to an x-axis, maybe like a sideways parabola, it's not a function anymore. So the other one was with respect to the origin. And we call that an odd function. And that's where f of x was negative f of negative x. Or typically how it's written, negative f of x is f of negative x. However you want to view that. So they're asking you to test, is the hyperbolic cosine an even function or an odd function? And you'll find that there is symmetry there. So then with symmetry and end behavior and that point at the origin, you should be able to construct a semi-decent graph. So sort of just tying back into prior knowledge is what that's doing. It's a new function, but hopefully a lot of this stuff we remember from algebra or pre-calc. But there's a reminder if not. Okay, any other questions on the homework?
Yes, it's 2.5 again, but question 13. Just as x approaches negative infinity is the one I was confused on.
Okay. So let me go back here. Okay, so the limit at negative infinity. We looked at one of these last class, where we said the general approach was to divide everything in the numerator and denominator by the highest power of x in the denominator. So we see that essentially there's two powers initially. We look at the x cubed here, and then we look at the x to the 6th, but it's under the radical, so it's really the square root of x to the 6th. Which is also x to the 3rd. So there was a shorter way of computing these limits at infinity, and there was the longer way. So if we look at the shorter way, we're just going to look at the leading terms here. Because the plus 8 out at infinity doesn't really matter, and the plus 3 under the radical out towards infinity doesn't matter. So are we all okay with that idea? It's a bit weird because we don't usually ignore the lesser terms until we start looking at limits at infinity. Okay. So let's take that expression and just simplify it algebraically. And then we'll come back up here and work with it. What's the square root of 64x to the 6th?
8x cubed.
8x cubed? What do y'all think? Anybody disagree with that? You should disagree with that.
Is it 4?
Let's say the error is here.
Well, there's a hitch in the get along because when you're like I did it the other way where you have you divide it by negative x cubed, but when you're using the radical, it has to be positive x to the 6th.
Right.
So you're ending up with a sign that's switched.
Exactly. Yeah, and there's so I don't know if you were getting like 2 for the first limit and positive 2 for the second limit. Was that kind of the outcome that you were experiencing, or?
Yeah, so mine was a little different, but basically I was getting a fraction, and then it's supposed to be -1, and well, it just wasn't.
Okay, so you have to remember when we'll come back up to the limit right now. So just pretend that we're not working with the limit at this point, and we're just simplifying that function. And I'm not specifying where x is at this point. We have to remember that our argument was motivated by what was the square root of x squared. And we said it's not the same thing as x. It's not equal to x, but it's equal to what? The what?
Is it x and negative?
Yeah, it's x and negative x depending on where x is, and we wrote that just like this, right? So what's this, let's just algebraically, what's the square root of x to the 6th?
Absolute value of x cubed.
Yep, absolute value of x cubed. Remember, x cubed can be positive and negative sometimes, depending on where x is. So we have to ensure that what comes out of a square root is always positive. You've never seen the square root output a negative number, unless it was the negative square root of something, right?
We're saying this is the easy way?
Yeah. Either way you approach these types of problems with the radicals involved with powers of x, you have to think about, you have to be cognizant of where x is, because sometimes it's positive and sometimes it's negative.
How do you
I
determine
feel
that?
like the hard way is easier.
But you still have to think, when I'm going out towards positive infinity, I'm going to divide by a positive x cubed.
Right.
And
you
when I'm
definitely
going out
do.
to negative infinity, I'm dividing by a negative x cubed.
Right.
That's really all it boils down to, right?
Yeah.
It just boils down to, if I'm approaching positive infinity, then you divide things outside of the radical by positive x cubed. Things inside the radical by x to the 6th. If I'm going out to negative infinity, it boils down to dividing everything by a negative x cubed. But inside the radical, it's still x to the 6th. So, I don't know, you could say all of those words and it's kind of like, what? But in practice, that's sort of how it unfolds. But in actuality, this is what you're doing. Whether you want to admit it or not, that's what we're all doing. So that's this function, the absolute value of x cubed. Again, this is in our notes, but it's defined as x cubed when x is larger than or equal to 0, negative of x cubed when x is less than 0. So really, you should have said the absolute value of x cubed, or even a negative x cubed would have worked if you were thinking about the context of the limit. Oops. So that's what it simplifies to when we don't know where x is. When we know where x is, then we're going to use one of these definitions, depending on where x is. Yeah.
So we have a negative 8x cubed.
Yeah, so for this limit, it'll be a negative 8x cubed. Since x is approaching negative infinity, we're running through all the negative numbers. So I'll say this, when x is less than 0, we have 4x cubed over 4x cubed. I'll just write it like this, plus 8 times negative x cubed. So we're using this part of the definition. Any questions or comments about that? It's important to know because sometimes you don't have to do this, right? Like if I took the square root of x to the 8th, I don't have to divide everything outside by positive and negative x to the 4th, right? Because x to the 4th is always positive. So it does make sense to talk about this. Because not all problems do you have to divide by a positive and a negative, depending on which direction you're going. So we'll just simplify this a little bit further. We have 4x cubed over 4x cubed. Well, let's just complete the denominator. We have negative 8x cubed plus a 4x cubed, so we have a minus 4x cubed on the bottom. So it just simplifies to negative 1. Meaning that, you know, we could have put all of this stuff, all of this work here and here in front of the limit, but we just chose to work with it separately and simplify it. So what we've simplified that to that limit, which is, of course, always negative 1. So I think the most simplistic and easiest way to remember these functions that involve radicals is that if you take the square root or an even root of something and get x to an odd power, then you have to divide by both positive and negative. And in that particular instance, the division by a positive x cubed, let's say, or a negative x cubed will correspond exactly to the infinity that you're approaching. Does that make sense? Is that, I don't know. We can illustrate that, but that's how it shows up in practice. But this is what you're actually doing. So I don't know if that's helpful or not. But if I said, like, just another example, if I said compute the limit as x approaches infinity on x to the 5th over the square root of 2x to the 10th minus 4, something like that, and the limit as x approaches negative infinity, same function. The sort of what we're thinking about on the side is, well, the highest power of, let's make this a little bit easier. The highest power of x in the denominator is the square root of x to the 10th. So over here, I'm going to think, what is the square root of x to the 10th equal to?
Plus 4 minus x to the 10th.
Yeah, it's the absolute value, because we get, if we say x to the 5th, that's not correct. X to the 5th can be positive and negative. We want to make sure it's always positive. But since we're approaching positive infinity, the things under the radical, I'm just going to divide by x to the 10th. Divide by positive x to the 5th up here. If I'm approaching negative infinity, I'm going to divide by negative x to the 5th. Still x to the 10th under the radical. That's really all of those problems like that. They always boil down to that. If you have the even root of x to a power coming out as x to an odd power. I don't know if that's helpful, but I know sometimes we want to look for shortcuts or easier ways to remember things. So that's about as easy as it gets, I think.
If it's x to the 6, it's an even number, we don't have to worry about that.
Right, right. So that, like, if it comes out as like the square root of, what's the square root of x to the 12th, and you say it's x to the 6th, then that's fine, because x to the 6th is always positive. When you plug a positive or negative number in for x to the 6th power, it's always positive. But if I plug a positive or negative number in and raise it to the 5th power, it's positive or negative, depending. All right, I don't know, I hope that helps. Does anyone have any questions or comments on that type of problem? A particular way you might think about it?
If you did it the easier way, you still have to keep that negative 4. It could just be between the leading terms. Like I would do 2x to the 5th.
On the bottom?
Minus 2 or 1.
No. So, like, as long as we're going out towards infinity, the minus 4 is insignificant.
Okay.
So if we're doing it the easier way, then let's just write it here. This function would be equivalent to x to the 5th over the square root of just 4x to the 10th, just leading term over leading term. Okay. And then that's when we would simplify this as x to the 5th over 2x to the 5th if x is positive or 0, or it's x to the 5th over negative 2x to the 5th for negative values of x. So you always have two different outcomes. each corresponding to the two different limits, positive and negative infinity.
That's right. Will you be saving those and putting this on?
Yeah, I will. I'll upload this. Yeah, it was. Someone pointed out that the 829 video wasn't posted, so I'm uploading that right now. Sorry, somehow that got overlooked. But yeah, I'll post these two. Other homework questions? Yeah.
On 18.
On 2.5 at number 18.
I don't get how the, like in this case, I don't get how the sign cancel. Because it came out to just one.
The limit?
Yes, so it'd be where k is a finite number.
Okay.
And the next part.
Oh, there's more than. Is that the only part?
No, there's 2 parts to that one, I think.
Okay, let's see if we can get those parts in there. I'll have to do this one at a time, I think. Oops. Well, we've already seen. We'll see how this unfolds, but capture both of these. Hopefully that's still legible. So we have this function 2t plus sine t over t, and it represents a system that varies with time. The existence of the limit ad infinity on this function of t, on any function of t, means that there is a steady state or equilibrium. So another, like a physical interpretation of a horizontal asymptote is that if, you know, like if I had this population function, let's say, if I had this population function, I would say, well, you know, I don't know, we're in trouble because the population just keeps growing, right? Maybe that's true for humans, but other animals, that's not true for. So what if I had this population function?
It's just growing at a steady rate.
Yeah, right. So we see that the steady rate is right here once it's horizontal. So this function is reaching this horizontal asymptote, but in terms of a population growth, we're saying that growth levels off at whatever this is, 200 million, whatever that happens to be. So that population does reach a steady state at 200 million. So that's a physical interpretation of a horizontal asymptote. Okay, the amplitude of an oscillator is given by A of t. Determine if a steady state exists and give the steady state. Okay, so really the first part says, for which of the following situation does there exist a steady state? So it's just checking that you know what a horizontal asymptote is and how that looks mathematically. So if I compute the limit at infinity on some function and get a finite number, then that finite number is my horizontal asymptote, i.e. my steady state. If as time progresses towards infinity, but the population or the function just keeps growing and growing, then there is no steady state reached, there is no horizontal asymptote reached. And if f of t doesn't exist and is neither negative infinity nor positive infinity, then, so what would a situation be like in choice C here? What would a situation be? I mean, you can think of physically or mathematically.
The population just doesn't exist at all. If we're saying that the horizontal asymptote doesn't exist, then the population itself doesn't exist, right?
Okay, right, yeah. So like, you know, this, as far as population is concerned, if we're going to talk about population, as t progresses on, the function, the limit as we approach infinity doesn't exist. So then you got to think about situations where limits don't exist. well, positive and negative infinity, that limit doesn't exist, but they're excluding that choice, right? The limit doesn't exist and it's not positive or negative infinity. So when's the only other occurrence that we've seen where a limit doesn't exist?
When you have steady oscillation.
Right, so like if it just kept oscillating back and forth, like a sign between 1 and -1. Also, I don't know why it would be, but if your population function was somehow piecewise, right, and you had like a jump, the left and the right limits don't equal. You know, those are the two instances where we've seen limits don't exist. Okay, so I hope choice A is fairly intuitive at this point, but because that's the exact definition of a horizontal asymptote. And so then we want to determine if the steady state exists, and if it does, what is the steady state population? So we need to compute the limit as t approaches infinity on a of t. Oops, that was all over t. Okay. We've ran into this a few times. At infinity, sine, cosine, what is their limit at infinity? It doesn't exist because out towards infinity, they're doing this, right? It's just always in between 1 and -1. That's really all we can ever say. So I think we wrote that in our notes. Limit at infinity on sine and cosine does not exist. So how would then we approach this problem? Yeah, so we can try the squeeze theorem. We can try to squeeze t sine t over t in between two well-behaved functions. So I'm going to write it like this: 2 times the limit as t approaches infinity. And let's just see if we can go down here. So if we have, for sure we know that the sine of t is in between 1 and -1. Okay, what else do we need to insert in here? We need to add t to both sides. So we're going to add a t here, add a t here. And then what do we need to do?
Add.
Divide by t. Divide by t. Divide by t. So is that reasonable? Is that inequality make sense? We can divide by t as long as t is not 0. So in this context, since t is approaching infinity, we're totally fine. T is so far away from 0 that it doesn't matter. We divide through by t. Then we compute the limit on all of our pieces. So what's the limit as t approaches infinity on our ends? It's not 0. What? Okay, so what's your reasoning that it's 1?
-1 plus infinity is going to be some arbitrary large number of infinity divided by infinity is going to be 1.
Okay, I would say that you're right, but your reasoning is not right. Infinity over infinity is not 1. Infinity over infinity we haven't talked about. We'll see in chapter 4. But infinity over infinity and 0 over 0 in terms of limits can have any value. So we can't reason that it's approaching infinity on the top and bottom, therefore it's 1. That's not That's not accurate. One of them could be growing a lot larger than the other. Okay, well, what if I ask you to compute this limit? What's the limit as x approaches infinity on x plus 1 over x? How would you compute that limit? First of all, what kind of function is that in terms of x? It's a rational function. So we need only look at what?
X over x.
X over x, leading term over leading term, right? And so we would say, well, leading term over leading term, here's the limit. X approaches infinity, x over x, it's equal to 1, right? Same thing, just change the x's to a t. We're going to ignore the -1. We're going to look at leading term over leading term. That limit is 1. Leading term over leading term, that limit is 1. So what is our limit for sine t plus t over t? It's 1. Okay? Does that make sense? Yeah.
What about your 2?
Yeah.
Yeah, what about our 2? We still have to figure that out. The hard part's over because we figured out this weird limit, what it was. That weird limit has to be 1. So the limit as t approaches infinity, t plus sine t over t has to be 1. Yep, and then we just multiply it by 2. Because we took the 2 out. We could have kept the 2 in this whole inequality process if we wanted to, but I think it's a little more straightforward to keep it out. Oh, well, we already said that limit was 1, so we'll just write that out. So I don't know that they told us what population numbers were measured in, millions or billions or whatever, but 2 is the steady state population. Or in other words, that function has a horizontal asymptote at 2. Maybe we can verify that. Oops. Probably too many, but no, sorry, divided by x. All right. Yep. So I mean, around the origin, we see that it's sort of larger oscillations, but as we zoom out, we don't see those oscillations quite as large anymore. Okay, so there's our horizontal asymptote, and the red is our function. Does anyone have any questions on that? Excuse me.
So I looked at like the help from the math lab, and it did it like the harder way where you divide through everything, and it like canceled out cosine pretty much right away.
Yikes.
Like it just went to 6. And I was just confused on how it even cancels out, or do they just like cosine?
So yeah, if we looked at it,
Sorry.
I think either way you approach that problem, though, you have at some point you have to think of the squeeze theorem,
Yeah.
because if we said, you know, let's look at dividing everything through by t on this function here. So if I just divide everything through by t like this, then I have 1 plus sine t over t all over 1. So it's just then equivalent as this is true as t approaches infinity. So it's just equivalent to this. So I don't know, is that what you were talking about? Like the longer way? Yeah. Either way, you get to the point where at this moment we have to think of the squeeze theorem being active.
But you said on our exam, you'll notify us when we need to use the squeeze.
Yeah, on your exam, I don't have any problems directly where you have to think, is the squeeze theorem applied here? And if so, what does that inequality look like? If this problem showed up on the exam, I would tell you, so I think it's worth mentioning, if this is an exam problem, I would say something to the effect of, given, what was it, minus 1 plus t over t is less than or equal to t plus sine t over t less than or equal to 1 plus t over t. So I would just straight up give you that, and I would say if you know that's true for all t, what is the limit as t approaches something? In this case, it's infinity of this function here. So what is that limit given that inequality is how the problem would be stated.
The answer is 1.
Yes. So this is how the squeeze theorem on exam 1 would show up. You know, something to that effect. Inequality is given, you have to find the limit. Any other homework questions? All right. So I know that took up a lot of time, but I think it's certainly worthwhile to talk about these things, especially the material that it's been a week since we've talked about. And I would encourage you that as you study that you do frequently go back to old stuff. I know it can be sort of frustrating trying to learn new stuff while you're revisiting old stuff, but the more you sort of work in old material, the better. It's just increasing exposure. So in 2.6, what were we talking about in 2.6? Continuity, yeah. 2.6 was about continuity. We looked at continuity at a point, and then we started looking at how do we define continuity over an interval. We saw that with some functions, like the square root function or piecewise functions, do have only one way to approach from the left or the right. So then we sort of talked about continuity in terms of left and right continuous, where we used one-sided limits. And then so we looked at this example just to see how that unfolds. And we first looked at the domain, the overall domain of that function, which we said was all real numbers. And we're trying to determine intervals of continuity. And I hope it's clear that the only thing that should be in question is that function continuous at 0 itself. Because all of the other intervals are completely contained within, you know, any of these intervals. So I've got this interval here, whatever. All intervals are contained within those two. The only issue is perhaps at 0. So we said, well, is f continuous at 0? We're going through the checklist. 1, does the function at that location exist? Yes, it exists. It was 1. And then we check the limit as x approaches 0, which requires us to compute a one-sided limit. And we're validating that through the domain of each piece. So we said, all right, well, if we approach 0 from the right, then I have to use the 3x plus 5 piece, and then that limit comes out to be 5. And then we stop right there and say, okay, well, I've computed the limit from the right, and I have a function value. So at this point, I can say something about right continuity, because I've computed a limit from the right. So we stopped there and said, all right, is that limit the same as the function value? It's clearly different. Therefore, the function is not right continuous. Remember, if the function is right continuous at 0, then what that means is that as we get up to 0 from the right, that we're able to include that as part of the interval where it is continuous. But we said it's not right continuous, therefore we're not including 0, so we put our parenthesis around 0 instead. Okay, yeah, I wrote too large. I'll erase this, but it might be something that you want to put in your notes. If we say that it is, for instance, right continuous or left continuous, at A, that means we include the endpoint with this or with this, depending on what direction you're approaching from. If it's not left or right continuous, we do not include the endpoint. So then we have our parentheses. And honestly, it's easier just to look at the function and the function value at 0 and use sort of an algebraic approach to that. But it's not technical to look at it that way. The technical aspect comes in with looking at limits from the left and from the right. Okay. All right, so I'm going to erase that. What I have here in red. If you need a minute to copy that down or want to copy that down, just let me know.
So we're saying that it's continuous on 0 and infinity. Is that the end answer to that question?
The overall question, no, because we have to look at the limit from the left as well. Because all we know is what happens as we approach 0 from the right. So we have half the story. We've got to look at what happens as we approach 0 from the left. Does everyone have what they need? Should try to make some room as well. This will work. Oops. Yeah, I'll go back and fix that. I just didn't leave enough space to write. Okay, so are there any questions on what we've done or kind of where we're at? I don't know what else I missed.
Limited is x of x versus that is not equal to f of 0.
Oh yeah, that's super important. Thank you. Everybody good with what we've done? We just modified the definition of continuity to speak about only from the left or from the right. Okay, so the next thing we have to compute then is the limit from the left. So we'll call that part 2 for checklist item number 2. So if we're approaching 0 from the left, then we have to use our top piece. So that is x squared plus 1. And the limit as x approaches 0 from the left of x on x squared plus 1 is what? 1. So is that limit the same thing as the function value at 0?
Yes.
Yes. So since the limit is the function value, what does that mean? It's left. It's continuous from the left. Okay, so let's write that here. Since the limit as x approaches 0 from the left on the function is the function at that value, f of x is left continuous. Left continuous. At x equals to 0. Yeah,
You can
Omar.
also tell it's continuous because if we have the 0 from the right, we would also get 1. And so since we have, they both match 1 from the left and 1 from the right, it would be continuous, right?
Well, no, remember, because as we approach 0 from the right, we got 5. Was that what you were asking?
Yeah.
Yeah. But you're right. If both of these limits were 1, then we would say it's continuous from the left and right. Yep. Okay, so we've stated that it is continuous from the left. So what's the interval on that it's continuous on? Including or excluding? Okay, good. F of x is continuous on that interval. So it's sort of a, like a word game, right? If I know where it's not continuous, then that tells me where it is continuous. So in both of these the instances, these left and right limits, that's often where you land. You say, well, it's not continuous here. Then you want to go ahead and explicitly state the intervals where it is continuous, since you know where it's not continuous. So this is really our answer for the intervals of continuity. Oops. Where is f continuous? Let's just summarize it then instead of. So our therefore f of x is continuous on those two intervals that we've listed. So what we're saying is that it's continuous on these intervals, and then I can hopefully visualize or clearly see that as I approach 0 from the right, that the function value or the graph, if you will, what happens there? Is that actually included in the function? No. And then as I approach 0 from the left, it is included in the function. Also, graphically, what would that mean? Since we're not continuous from the right at 0, but we're continuous from the left at 0. If we looked at that graph, what would that mean for the two pieces? Yeah, are they together or are they separate?
They are separate.
They're two different pieces, right? If it were continuous from both directions, that would indicate that the graph meets up at that location. So we have two different pieces, and let's see, what was this one? I think, yeah, well, yeah. This graph. Somewhere. So there's the graph of the function we just worked with. Does anyone have any questions on that example? So for time reasons, I think we'll skip the next example. It's very similar. Oops. All right, maybe I already, no, it's here at the bottom. So we're going to skip this example. Really the purpose of this example was to show you the other outcome where a graph has the two pieces that are actually connected. So let me just state here, if you do end up working this out, remember one-sided limit at a time, you make a conclusion each time you compute a one-sided limit. So the limit as x approaches 1 from the right on this function is equal to the function value at 1, so it's right continuous at x equals to 1, i.e. the interval of continuity would be what? If I'm right continuous at 1, what does my interval of continuity look like?
1 to infinity, including 1.
1 to infinity, including 1. So I can approach 1 from the right, and I can include that. Also, the limit as x approaches 1 from the left on that function is also the function's value at 1. It's left continuous. Oops. It's left continuous as well at x equals to 1. What's the interval of continuity then if it's left continuous at 1? Negative infinity to 1, including 1. So, but would we stop there and say, well, there's the interval of continuity. What is the actual interval of continuity?
Negative infinity to infinity.
Yeah, right? So we're seeing from this side of 1 that we're including that. And then over here we're seeing from the other side of 1, from infinity to 1. Right, continuous. I mean, it might be more helpful if I drew it the other way, but the idea is that since we're continuous on both sides at 1, the function is also continuous at 1. Okay. I don't know if that visual helps or not. So really in an instance like that, we need to look at putting those together. So f of x, we would say f of x is continuous on that interval. And that would be our answer. Yeah.
How do we know when to use the closed brackets at 1? So like, how do we know when to include 1 in the interval of continuity?
If it's not continuous from the right, we would have a parenthesis there. If it's not continuous from the left, we would have a parenthesis there. And again, we see that coming through like this, where the one-sided limit is not the function value. Okay, yeah. So this is an example. If you were to graph that, you would see that the pieces do actually meet. Okay. Any other questions or comments on that? All right, let's take a break.
You don't have to work.
All right, well, I'm trying to upload that video from the 29th again. I don't see it on the list. It says there's 6 videos there, and every time I've uploaded it, it says that it's a duplicate. So I don't know what's going on, but I'll figure it out. All right. So the next theorem is going to tell us something about continuity for functions that involve roots, even and odd roots. So m and n are positive integers with no common factor. M is an odd integer, and then f of x to the n over m, which means we're taking the mth root, or an odd root. So it's basically saying all odd roots are continuous at all points where the inside function f of x is continuous. Okay. So what that says is taking odd roots. Odd roots do not change continuity. That's basically what that's saying. But if m is even, then we're taking an even root of a function, then it's continuous at all points, continuous where f is continuous and f has to be larger than 0. So it's saying that even roots are continuous it doesn't change the continuity of f. If f is like not continuous at 1, then the square root of the function is not continuous at 1. But when we take an even root, it does add an additional restriction to where it also has to be greater than 0 or positive. So even roots are continuous where f is continuous and positive. So notice it doesn't say anything about continuity at 0. It doesn't say it's continuous where f is continuous and where f of a is larger than or equal to 0. It's just strictly speaking of positive values. So, a function where we're taking an even root and we have to be mindful about whether it's continuous at 0 would be just the square root of x. For example, if f of x were the square root of x, is f of x continuous at x equals to 0? Even though we can compute the square root of 0, is the square root function continuous at 0? No, how come?
Because that's where it ends. Like it's only right continuous, I guess you could say.
Yeah, because the square root function sort of ends there, right? The domain is from 0 to infinity. As far as continuity goes, certain instances, especially with even roots and other types of functions too, but even roots, you have to be mindful of basically the domain of the function. Can I approach it from both directions? No, the function is only continuous continuous on this interval. And just, a short answer here is no. It's not continuous on both sides. So that's, the part of the theorem that doesn't include 0, f of a is larger than 0, is because we have to be mindful of what happens when it's 0. Sometimes there's continuity there, sometimes there's not continuity there. So if we looked at kind of a similar function but not quite identical, if we looked at the square root of the absolute value of x, then we are continuous at 0. So just, it matters what's under the even root here. And so we're going to apply that theorem to the next example where we're looking at the square root of 9 minus x squared. So for what values is the function continuous? We have an even root of the function 9 minus x squared. So theorem 2.13. We'll just start off by saying theorem 2.13 states that our function is continuous where 1, the function on the inside is continuous, and 2, where the function on the inside is strictly larger than 0.
And essentially be all numbers except 9 square root, 3.
3.
Right? It'd be all values except when x equals 3.
And negative 3, right? So when we look at 9 minus x squared, where is 9 minus x squared continuous? Just as a function by itself, 9 minus x squared.
Everywhere.
Everywhere, because it's what type of function? Polynomial. Yeah, polynomials are continuous on all real numbers. So we'll just say that again. 9 minus x squared is a polynomial. And thus continuous on all real numbers. So we had a theorem that stated that. You don't have to remember the theorem's name or, verbatim what it said, but it said polynomials are continuous everywhere.
Could that be the same, I guess, wording as infinitely continuous? Like just in that sense right there. Like
Yeah,
in
I
our last
suppose.
example too, infinitely continuous.
Yeah, I guess you could think of it that way. It's not referred to that way, but yeah, I mean, it's kind of essentially wherever you go, it's always continuous. Okay. All right, and then the second question is, when is 9 minus x squared larger than 0? When x is greater than 3, do y'all agree with that? It's a 9 minus 16. Is that positive? No. Okay, so that's not quite accurate.
Would it just be less than 3?
Less than 3?
In between -3 and 3.
In between -3 and 3. How would we know for sure?
Plug and play.
That's exactly it.
Yeah, I guess that's highly inefficient and very limited. So there's two ways. One, we can think about how did we solve polynomial inequalities, or with quadratic, especially, those should be pretty easy to graph. We've got a quadratic that's negative, it's opening down, and we're adding 9 to it, so it's shifted up 9 units, right? So we reflect it, and then we shift it up 9 units. So if we were just to simply look at the graph of that quadratic, let's say that's 9 right here. Then we're looking at that, and everything above the y-axis, or sorry, the x-axis, this is where it's larger than 0. So we have to describe this interval. It's larger than 0 here to here. And then it's beneficial to know what those points are that we're not including, because that's where it's identical to 0. So that's where we find the zeros of that function at -3 and +3. So let me just modify this. So 9 minus x squared is larger than 0 on the interval -3 to 3.
Would it be brackets or the square brackets including 3?
But we're not including 3. It's square brackets if it's larger than or equal to.
Oh, okay.
Yeah. Remember, the other way to do that, to solve inequalities, you've got to figure out where your function equals 0, and then you've got to test numbers to the left and to the right and in between. So we would say, well, 9 minus x squared is 0 when x is equal to plus or minus 3. And then we draw this. Here's -3, here's +3. What happens over here, what happens here, and what happens here? And you just plug in values. So at least if you're going to plug and chug, you should go with that approach as opposed to just plugging, all kinds of numbers in. So if I plug in 4, 9 minus x squared is negative. If I plug in any of these numbers in between 3 and -3, 9 minus x squared is positive, and 4, 5, 6, etc., it's negative. So in effect, you're looking at the graph when you come up with that chart. I know here it's 0 and here it's 0. So it starts below, crosses, now it's above, crosses again, now it's below. So that's exactly what we illustrate there with just the graph. Again, larger than 0, not larger than or equal to. So that's what Theorem 213 says. It says that the square root of 9 minus x squared was continuous everywhere 9 minus x squared is continuous, and where it's positive. So we started off by saying it's continuous on all real numbers, but it's only positive from -3 to 3. So that's kind of the working interval of continuity that we have now. We've restricted all real numbers now to -3 to 3. And then so we want to know then, we have to check ourselves because the theorem doesn't tell us if it's continuous at the endpoints. Okay. So let's just write what we have so far. We know that the square root of 9 minus x squared is continuous on -3 to 3, not including, by Theorem 2.13. Are there any questions on what we've done there? All right. So we need to state this, but Theorem 2.13 does not tell us anything about continuity when that function is equal to 0. So don't get the f of x that we're talking about in Theorem 2.3 confused with the f of x that we're dealing with. F of x in the Theorem 2.13 is simply the function on the inside of the radical. Okay, so since the theorem doesn't tell us anything about continuity when the function's 0, for us, the function 0 at the endpoints, 3 and -3, it's up to us to check that left and right continuity. So So we now have to check continuity at the endpoints. X equals to -3 and x equals to 3.
So why are we limiting the continuity to just the -3 to 3?
We're just simply basing our work off of that theorem, and that theorem is very generic.
Okay.
So it just means for any function you're taking the even root of, the best we can say is that sometimes you have weird things happening when the inside function of the square root, or the even root rather, is identical to 0. You might have some weird things happening. And one weird thing that we saw is that the function might only be continuous from one direction, like the square root of just x.
Right.
Mm-hmm.
I mean, if like for something like this, wouldn't this one just be it'd be continuous from -infinity to infinity? Wouldn't it just be that simple?
No, it's not, because, and maybe we should pause and take an aside to say, what is the function y equals the square root of 9 minus x squared? So what is that function? The parabola? So aside. So the square root of 9 minus x squared equals to y. What is that? Or what's the graph? Describe it in words, or we can describe it as a picture. It's not a parabola if it's 9 minus x squared is the parabola. So remember, the theorem said that the function on the inside of the even root is continuous and has to be positive. So that's why we sort of took this detour with item 1 and 2 here. We said, where is the function on the inside continuous, and where is the function on the inside positive? But overall, we want to know, where is the function root 9 minus x squared continuous? So the square root of 9 minus x squared, what are we, does anybody know what that is? It's what? Not one side of the parabola.
It's a semicircle.
It's a semicircle. It's one side of a circle, one half of a circle. So we square both sides. And then we add x to both sides, x squared rather. So do you recognize that formula? X squared plus y squared equals to 9. It's a circle centered at 0, 0. With a radius of 3. But is it the whole circle? No, because if I said, hey, here's the equation of the circle, we all agree that that's a circle. And then you said, well, I want to explicitly know what y is. You would solve for y, since y is squared, you would say it's plus minus the square root of 9 minus x squared, right? So that's the full circle, plus root and the minus root is the full circle. We're only talking about y equals the positive root. That's our function, the positive root. So y is positive, it's the upper or lower half of the circle.
So it's just going to be a 3, 3, 3.
Yeah.
Y plus 3 minus 3.
Yeah.
Plus 3 is going to be that half circle.
Yeah, above the x-axis, because y is the positive square root. So your circle is above the x-axis. Okay. This is the complete circle.
Oh, so it's just, the graph is just the circle in quadrants 1 and 2,
Mhm.
not 1 and 4.
Right.
Okay.
But y equals root 9 minus x squared is the upper half. where y is positive. If we had y being the negative square root, then that's the bottom half of that circle, when y is negative. Okay, so that's what we're dealing with. The function we're asking about continuity on. Whatever. Good enough. That's the function we're looking at. Here's -3, here's 3, here's a y value of 3. So we want to know, where is that function continuous? Yeah.
So does that mean that you can typically just calculate what's on the inside of it and that'll give you the same answer, or is that just for this problem?
Yeah, but you also, remember when we first started talking about continuity, so the vast majority of these functions, continuity and domain, are kind of the same issue. So if it boils down that you know the domain of this function, then yeah, the function is continuous on its domain. But not all functions were continuous on their domains. What we saw with that piecewise, the first piecewise example showed us that it wasn't continuous on its domain, right? It wasn't continuous at 0, even though the function, the piecewise function's domain was all real numbers. Yeah.
So I understand that it's plus minus 3 because it's the square root of 9, but can I really quickly just see the arithmetic to get there from like where we decided that it was
Plus or minus 3?
Plus or minus
Sure.
3?
Yeah, so then when we were solving that inequality, we said, well, let's talk about, first of all, where it's 0. Because before we talk about where it's positive or negative, we find out where it's neutral. And then once we know where it's neutral, then anywhere but those points, it has to be either positive or negative. So when we solve this, we add x squared to both sides, and then we have x squared equals to 9. And then when we have something squared equaling a number, we have to take the positive and the negative root of that number. So I guess that's one way to see that algebraically. The other way to see that is to say 9 minus x squared, that's the difference of squares. So we factor that as 3 minus x times 3 plus x. So 3 minus x equals 0, or 3 plus x equals 0. So yeah, I guess there's two ways to think about it. Okay, so we are dealing with the upper half of a circle centered at 0, 0 with a radius of 3. We said that for now, what we know is that it's continuous from -3 to 3, and we need to check the endpoints for continuity. Okay. Can I erase that? So now we have to check for endpoint continuity, which means we need to check 1, what is the limit as x approaches -3? And which direction can we approach -3 from? The right. We see that from our interval, right? From -3 to 3, I can only approach -3 from this direction, +3 from this direction. So what is the limit as x approaches -3 from the right on the square root of 9 minus x squared? 0, yeah. It's the square root of 0, which is 0. So the limit by itself doesn't tell us anything about continuity. What else do we need to know before we say it's continuous? I'll give you a hint. It was the first item on continuity checklist.
The function value.
Right, the function has to exist at -3. So what is f of -3? Also 0. So the limit as x approaches -3 from the right on the function equals the function at -3. Therefore, it is right continuous at -3. If it's right's continuous at -3, what do we do with our interval? We put a bracket around -3. So we now know f of x is continuous on -3 including up to 3 not including, because we still haven't computed the limit as x approaches 3 from the left to compare that to the function value. So that's our next computation. What happens as we approach +3 from the left on the square root of 9 minus x squared? Well, that limit again is 0. F of +3 is also 0. We put those two pieces together and we say f of x is left continuous at x equals to 3. So then we put it all together. Therefore, the original function that we were given, square root of 9 minus x squared, is continuous on the closed interval from -3 to 3. So that's our overall conclusion. So it was pretty lengthy, but some of it was sort of an aside. What does the function look like? How do we determine where the inside function is larger than 0? And what you see is that if I looked at the function itself, that's its domain, right? That's that function's domain from -3 to 3, including 3 and -3. So the issue of continuity and domain, like I said, are similar for a lot of functions that we look at. But the idea of continuity is a lot more technical and complex than the issue of a domain. What can I plug into the function? You just figure it out, right? But where is this function continuous? Then I have to compute limits. Oftentimes they're one-sided limits, particularly when even roots are involved. And so that's what all of our work sort of solidifies and ties the fact that this function's domain is the interval of continuity as well. So I think with these last couple of examples with the piecewise and this example, you probably miss doing these things algebraically, because I think it was a little bit easier to determine, do the pieces connect algebraically, right? And just, are the y values the same is all you looked for, right? And what's the domain of this function? A little bit easier of a question to answer. Anyhow, questions about this example? All right, the next theorem just covers, where is it? Is it down here? I hope. Nope. Well, all right. I'll put it in your notes. That's part of the reason I gave you that handout dealing with the trig functions and the inverse trig functions. This will be in your notes. Sorry it wasn't already there. I don't know what happened to that. This theorem covers sort of a lot of different functions for us, and it says all of these functions here are continuous on their domain. So then of course it boils down to, well, what are the domains for these functions? If you know the domains for these functions, then you know where they're continuous. So for these, I'll just say see the handout. I really hope you remember the domain for exponential and logarithms, but it's okay if you didn't. We'll write it here. Exponential functions, their domain is what?
Negative infinity, infinity.
Yeah, we can plug in all real numbers into our exponential functions.
What is b to the x? Is just the same?
Yeah, so b is larger than 0
Oh, right.
and not equal to 1. And how about the logarithm? What's the domain for our logarithms?
All numbers higher than 0.
Yeah, every positive number not including 0. And then your handout has the domain for the trig functions and the inverse trig functions. And that's convenient in the sense because if it asks us where inverse sine is continuous, then really there's no reason to compute a limit in that instance. Because we can say, well, that one theorem we talked about in class said that inverse sine was continuous on its domain. And I know the domain of inverse sine is -1 to 1. So we take care of a lot of stuff with that one theorem. And that basically covers the types of functions that we see. The list of continuity, we looked at polynomials, then rationals, and then we looked at other algebraic functions that involve like the square root of x to the 6th. And then we come in with this theorem and our continuity laws or theorems as well. And it sort of puts it all together. We sort of now have this holistic picture for most of the types of functions that we deal with and how to find their intervals of continuity. Of course, the only thing that changes if I say what's the interval of continuity for the natural log divided by sine, what's the interval of continuity for that, then you remember, okay, well, natural log is continuous on its domain and sine is continuous on its domain. Then you have to remember a little bit of algebra that says what's the domain when you divide two functions? You have to look at the intersection of their domains or what they have in common and exclude where the bottom function is 0. So, you still have to remember some of that stuff, but then this sort of kind of closes the loop on continuity for basically any function that we'll see in this class. Okay. I do have another example to work, and it is related to continuity in the sense that when we're able to directly plug something in and evaluate a limit, that's based on the idea of continuity, but also sort of testing our other skills from previous material. So let's compute the limit as x approaches pi over 2 on the function 5 times sine x minus 1 all over cosine squared. So the first thing we should do with limits is to try to evaluate them directly. So by direct substitution, what would this limit come out to be? Do what? It's all over 0. Because cosine of pi over 2 is 0. Numerator is 0 too. Sine of pi over 2 is 1. Minus 1 is 0. So we can't make any sense of that. So then that tells us, well, we've got to simplify it or manipulate this somehow.
Just change it to the 1 minus sine squared theta.
Okay,
The
so
denominator.
the
more
denominator.
specifically.
Excuse me. Yeah, if we took cosine squared and used the Pythagorean identity to write that as 1 minus sine squared, does that help? So I'll just take this down here. and write cosine squared is 1 minus sine squared. So if we put that in place of cosine squared, would that help us out? Not initially, right? Because 1 minus sine squared is still 0. But there's something we can do with 1 minus sine squared that we can't do with cosine squared, and that would be do what? It can cancel out, but not immediately, right? Because up top we have sine minus 1, and here we have 1 minus sine squared. Factor it, right? So how can we factor 1 minus sine squared? Yeah, it's just a difference of squares, right? We have 1 minus sine times 1 plus sine. Okay, so if we put that in place of cosine squared, and we see there's potential to evaluate this limit by canceling those factors out. Sine x minus 1 on top, and one of these factors here that we wrote out. But again, we see that that isn't exactly the same. How do they differ?
Versus sine minus 1.
Yeah. So the numerator is sine x minus 1, and this one here is 1 minus sine x. So they're not exactly the same factor, but writing this in this manner, we'll say that, all right, this is 1 minus sine times 1 plus sine. Okay, so that's kind of where we're at. Right, yeah, it's because they're opposite, aren't they? This is a positive sign and a negative 1. This factor is a positive 1 and a negative sign. So they're exact opposites of each other.
Can't you just take the negative and put it outside of the parentheses? And when it'd be negative 1 plus sine x, which would equal sine x.
Yeah, that's right. So if you're going to cancel this out, you just have to know that they're opposites. Or you can, rewrite this again algebraically to see that you do have a factor of negative 1 left over when those two things cancel. So I'm going to do this down here.
So it cancels, but instead of having 1, you have a negative.
You have a negative 1, right? Because they're opposite. So I'm just going to factor a negative 1 out of 1 minus sine x. So sine becomes positive, and 1 becomes negative. Now, this factor and the factor in the numerator are the same. And so what we're left over with is, on the bottom, is negative 1 times 1 plus sine x. Again, if you're just looking at it this way, you've got to just be careful that these factors cross out, but since they're opposites, it's not 1, it's negative 1. So whether we want to put the negative 1 in the bottom or the top, it doesn't matter. Let's just say we have negative 5 over 1 plus sine x. Yeah, so since we eliminated the problem of dividing through by 0, we can evaluate this limit directly. So as x approaches pi over 2, our function approaches what?
Negative 5 halves.
Yeah, negative 5 halves. So that's negative 5 halves. So the issue with trig functions, as you know, is that there's so many identities, right? You spend a lot of time looking at prove that this is equal to this, and they're not common identities. But the common identities that show up are definitely the Pythagorean identities and the double angle identities. So you should know those for sure. You should know these. With that Pythagorean identity, all of the other two come out of that one. So if you just remember that one, I think that's fine. But you have to remember then to divide all of it by sine squared, to simplify the reciprocal functions, and then divide all of it by cosine squared, simplify those reciprocal functions. And that'll give you the other two Pythagorean identities. Yeah.
Now, this might not be related to what we're doing, but if we use Hyperbolic rule, we would still get negative factors, right?
Yep. Right. And L'Hopital's shows up in 4.7, so that's a significant ways away. But it's a little bit easier when we get limits like 0 over 0 or infinity over infinity to use L'Hopital's. It's just we're operating under the assumption that we don't know what that is yet. So we have to do it the harder way. So 1 plus tangent squared is what? Yeah, secant squared. And 1 plus cotangent squared is cosecant, yeah. Cosine. So those are your Pythagorean identities, and then your
Just about every trig identity comes from that sine squared plus cosine squared equals 1.
yeah.
In certain ways, you can
Yeah.
re-manipulate the equation, change the way certain things are expressed. And
Right.
You can make almost
Infinitely many.
Yeah, I mean, you can make it. You don't have to sit there and memorize that whole page of trig identities.
Yeah.
You just got to memorize that.
Right, and if
How
you
to
want to do
change
some
that.
work to remember the other identities,
I
yeah.
didn't want to.
Yeah.
I want to memorize that whole damn page, so I just,
Yeah.
started to look at that, and then would just find, if I had a problem I didn't know, I'd just set that up and change it to what I
Okay.
wanted to solve. And
Yeah. Yeah, I mean, it's
it worked out
definitely, you could definitely approach it that way. It's not quite as efficient of just knowing them,
Right.
but certainly,
more time,
an
but
approach,
less
yeah.
memorization,
right.
give and take.
If you remember in the XY coordinate system, cosine of theta described what coordinate?
X.
The x coordinate, right, on the unit circle. Remember cosine of theta was x over r? So the radius for a unit circle is 1. So cosine of theta would give us our x coordinate, and the sine of theta gave us our y coordinate, right? So if we see when we see sine squared theta plus cosine squared theta equals 1, essentially we're looking at y squared plus x squared equals 1, which is our unit circle. So that's exactly where the sine squared plus cosine squared equals 1 comes from, is the fact that we're on a unit circle, and that's the equation of the unit circle. Anyhow, sine 2x, anybody remember that one? Somewhat common. These things are a lot more common in Calc 2, for sure. That's 2 sine cosine. And then cosine of 2x. There's actually three identities for this one. Do what? No. It's cosine squared minus sine squared. Or 2 cosine squared minus 1, or 1 minus 2 sine squared. So this, these are fairly common. There's some other ones that come up later in the semester, but just because I'm saying that these are common doesn't mean that other ones don't show up. Okay. There's two other things that we need to address in 2.6. One of them is just the types of discontinuities that we see. There's classifying discontinuities. Discontinuities, yeah, sure.
Is this still 2.6 or is this like? Is this still 2.6?
Yeah, 2.6. So there's three of them. We have a infinite discontinuities, and those are like vertical asymptotes. There's jump discontinuities, when your function jumps. Like that. And then there are removable discontinuities. We've since been calling them holes, but technically they're called removable discontinuities. Just think about the algebraic process when you cross out a factor on a rational function. The factor or factors that you crossed out gave you a hole, but it's really that you're removing that infinite discontinuity and it turns into a hole. So removable. And depending on where you look, you might get other classifications. They might talk about endpoint discontinuities. Sometimes they call infinite discontinuities, essential continuities. There isn't really a standard agreed upon verbiage for discontinuities. It's just the types are agreed upon, not the language, if that makes sense. Huh? Yeah, I think there are a few things in math that aren't established as it's always this way, but by and large it is. And definitely different than like languages, right? Or sciences, or people quibble about stuff.
Why it's not spelled S-T-O-U-G-H.
And why is what not?
Stuff isn't spelled S-T-O-U-G-H. It makes sense.
Yeah. So, yeah, sorry, I don't know what happened here. These two slides are totally missing from the notes. But we're going to look at one implication. There's many implications, there's many theorems based on the idea of continuity, but one in particular that we're going to look at is the intermediate value theorem. And so I do apologize that's not in your notes. Again, with these theorems and definitions, I don't expect you to know them verbatim, but the main idea is what is the takeaway from these things. Typically how that works out is, in practice, how do we work problems that require us to use the intermediate value theorem or whatever. So it says suppose f is continuous on some closed interval AB. And then all of this is based on the fact that the function is continuous. So that's our assumption. L is some number between these two y values, f of a and f of b. So if we know that we've got these two y values, there's some number in between those two numbers, f of a and f of b, then there is at least one number on the x-axis, if you will, in AB, so that f of c gives me that L value, or gives me that number on the y-axis. So if we think about it graphically, like let's say, we're looking at some function. And notice this theorem doesn't say we know much about the function other than the function is continuous, and we know these two y values of our function. So let's say, for argument's sake, here is f of a, and here is f of b. And I say, well, there's some number in between f of a and f of b, right? Does that make sense? Such that there has to be an x value that gives me that L. There has to be some input down here on the x-axis that they're calling c, so that when it's put into the function, gives you that L. Now, notice that wouldn't be true if the function was not continuous. But since the function is continuous, we know that not only does it have, let's say, this point here at f of a, and this point here at f of b, but since we know it's continuous, we know the function is totally connected and uninterrupted in between a and b, right? So it's the idea that this function is continuous from a to b gives us the fact that any number in between a and b has to be generated by some x value called c. So any number L has to be generated by plugging c to our function. So there's a, it's a little bit more accurate here. But that's not true if the function's not continuous, let's say. If the function's not continuous in between a and b, then we could have a situation like that, right? Where, yeah, this L is in between these two y values, but there is nothing that I plug into that function that gives me that value of L. It's only because we know that this function is continuous throughout that happens. Okay. And just be careful of the wording. It says there exists at least one C. I'm very sorry that this didn't come out. I know it's a lot to write. So here's an example of an L value in between f of a and f of b, where it's not generated by some x value. The function isn't continuous. Here's the other one. Oh, here's the other one. This first one on the right was something that kind of similar to what we wrote down, but the one on the the one on the right rather gives us a sense of when we might have more than one C value giving us the same Y value or same L value. The theorem just guarantees at least one.
What are we saying L represents?
Just some Y value,
Okay.
specifically in between f of A and f of B.
Okay.
Because A and B are the endpoints, we know the function's continuous from A to B. And so notice all three of those functions that are shown there are just shown in between A and B. We say if I know the function's continuous in between those two x values, A and B, then whatever two y values I look at, all of the y values have to have that property. Like this y value here, call it m, that y value has to be generated by some x value too, call that d. You know, and we can keep labeling all of those y values in between. All of these y values have to be generated by some x value. And it's the intermediate value theorem. It just says if you've got a continuous function on a, b, then the function itself takes on all intermediate values in between a and b. In fact, that's how your calculator or that's how graphing software plots graphs and why you don't see holes in your graphs. because your calculator just plots a few points. So your calculator, if you tell it to graph like x squared, all your calculator is going to do is plot a few points. But then the machine assumes that it takes on all intermediate values in between those points. And it just fills this in like that because it's just assuming that it takes on intermediate values. So intermediate values just mean all of the ones in between, all of the values in between. And so that's, if this function had a hole in it, your calculator doesn't show you that because until you tell it specifically where you're at, it doesn't tell you anything about, oh, well, this thing's undefined there. As far as the graph goes, it just fills in the dots and it always assumes. Okay. So a couple of things. I'm going to abbreviate the intermediate value theorem. Does not tell us what C is. It just tells us that that possibility exists, but it's not going to tell you where that C value is. Also, if the intermediate value theorem is inconclusive, then there might still be a C that gives you that L, and there might not. But if the intermediate value theorem is inconclusive, you don't just totally dismiss that it's not a possibility. If it's inconclusive, you can't say anything about it. It's still possible to be there or to not be there. There might still be a C in AB such that so if it's inconclusive, don't make any conclusion. Inconclusive means that you cannot make a conclusion, right? So if it's inconclusive, don't say, well, there is a C still, or there isn't a C. I know that for sure. That's never going to be the case. If it's inconclusive, then you've got to use something different other than this theorem, because this theorem told you nothing. I think we'll stop there before we actually look at a specific example of how this applies. Do y'all have any questions before we go?
You have your hours tomorrow, your office hours?
From 1 to 3. Yep. All right, see ya.